Good morning for everyone. Give me a second. I just find my presentation. Okay. So I didn't know what kind of listeners I can get here. So I will give you some notes also about general machine learning to understand how we can put this idea, where to put it. So maybe something will be quite easy to, or maybe repeated, but I hope we can also talk about them and try to think about them from other point of view. So the idea, well, everyone, I hope that almost everyone know about the uh, machine learning, but I will just give you well, I think you, yeah, oh, sorry. So we will talk about today, we will talk about mainly supervised learning, but I remind you that we have supervised, unsupervised, and reinforcement as a three. It's like agreed general division, but of course, maybe you can find some change lately, so we can maybe erase margins a bit. So just to remind you, it's a very nice index of different companies that appears, startups and also big companies in machine learning and artificial intelligence in 2022. And if you see this index in 2023, you will see that almost all company changed. Something new happens. So we are living in a period of revolution, I think, where changes happen so fast that it's difficult to grasp what is going on, but we will definitely see this in our everyday lives sooner or later. So also another interesting topic, if you didn't knew about this, it's a deep index. It's a great thing. You very smart people. They gather all possible application of AI ML in our everyday life and how it's changed, and they group it in different areas. So you can just read what actually happens here, and talking about application and uh, how we can feel this because it's a bit a paradoxical thing going right now, that we have a constant growth, a lot of money invested, and as you know, Nvidia right now is growing very fast because they want to build specialized chips, especially for suitable for training of large language models and so on. But it's not obvious how this actually contributes to our life, how to, well, simply put, how to make money running a large language model or generating images, because obviously it changed human labor and changed our landscape of work, but how we can use it. Um, well, I like this application a bit. It's not about money, of course, but as you know, recently there was first success in the decipher of scrolls from Herculanum. 2,000 years ago, Vesuvius made eruption, and the huge city of Herculanum, big city of Herculanum, it was city for very wealthy Roman people, was covered with ash and preserved this way. And for example, there is a library of quite wealthy and famous Roman, and this library contains few thousand scrolls, and these scrolls were carbonized. So now, what they actually did, they can't uncover them because it will destroy them. So they tried special infrared spectrography to create a 3D model of this scroll. And when you have different angles, then this beam of light, they go differently through the just paper, not paper, but pergamon, but it's not matter, it doesn't matter which. And when it was actually written a letter, it goes slightly different. So you can see these changes in the 3D model, and they launch a competition for ML engineers to create an algorithm how to decipher of this old scrolls, which mostly just lost for now. Also, I know that every one of you probably know about AlphaZero and DeepMind approach. When you have this, when you have this algorithm which plays almost any game, any rule-based game, and some even not rule-based, but with infinite possibilities. It's like well, chess, Go, and shogi was solved very, very nicely, and then they go to they go to StarCraft and create an algorithm which actually can fight StarCraft, well, with some limitations, but nevertheless. So it was quite good. And then they try this approach to analyze folding of different molecular level I don't know, elements. So that's how actually machine learning can be used not only for fun and understanding the limitation of people or human, but also to actually create something very important for us. And when we say about, well, basically when you have supervised learning and supervised learning, you have this basic task, which for supervised learning is classification and regression, and for unsupervised learning is dimensionality reduction and clustering. And I hope you know about this algorithm, but maybe I need some I need some response, so um, I will not spend too much time on this. But I know I will tell you about linear regression in any way, because that's what I want to do. So when we talk about general machine learning pipeline, usually, well, we can divide it on following steps. So first we accrue data, yeah, as much as you can usually. Then you pre-process this data. As this data, by this I mean perform some exploratory data analysis, see some look for dependencies, look uh, for the values that are missing. We try to replace them. We try to understand is there any issues with the data, how can we fix this, and so on. Then we perform train test split and put something in safe place for validation, and then we build our model, and then we evaluate final model based on test set. This is quite easy. And in this way, we actually came to very complex and non-obvious models. And these complex and non-obvious models, actually, it's not easy to interpret, to understand. So when you have some bagging of different trees, or blending or stacking of some models, fully grown trees, and so on. Or maybe you create a boosting, or create a few models and then create an aggregation of them. And normally you can create a very big model, a complex model, and this model will perform quite good on your validation set, and you can even win a Kaggle competition with this model. But it's really difficult to understand what is going on inside this model. So the model is making prediction, but why it making prediction is not obvious anymore. So that's the case. Interpretability, or we have different actually names for this. We can talk about trustworthy AI. We can talk about explainable AI, about interpretable AI. So this idea that interpretability is the degree to which a human can understand the cause of decision. Because if you don't understand the cause of decision, that it's really it's really not easy to trust such a systems, and it's not obvious how we can actually take them into our lives if you don't understand decision made by this model. So that's the idea of interpretable machine learning, that this is a useful umbrella that captures extraction of relevant knowledge from machine learning model. So that's the idea that we can use machine learning model, build some relationship, and then make some simplification for people to understand of this new model. So for example, maybe you know that recently we used, well, some researchers used the idea of Alpha 3 of this algorithm to create a new algorithm of matrix multiplication, which is better than most of than humans did before. So, and when its algorithm is actually found, developed as a created by pieces of basic operations, people they read it and say, "Oh, okay, it's a good algorithm. Now we know this." And I actually highly recommend you this book, Interpretable Machine Learning: A Guide for Making Black Box Models Explainable by Christoph Molnar. So you can read about this more, because part of my presentation is actually built on this book. So in some cases, we don't need interpretability. So when we don't need interpretability, uh, then, well, in a few cases, by the way, as I see your rules that you use a special tool for asking questions, so questions can be asked only in the end or revealed at the end, or you will read it when it comes.
I can read them as they come.
Oh, okay.
It's a
So,
bit repetitive.
but no questions for now. Okay.
There is currently no questions, but if there will be any, I'll ask them.
Okay, thank you. So when we don't need interpretability, if the model has no significant impact of our life, at some, well, if it just generate funny pictures, that maybe we don't need it. If the problem is well studied, so if we knew, for example, for recognition of handwritten symbols, we know exactly how this model are working in general. So if we build more accurate one, it's not important how it make prediction, because more or less we know how it is done, how we look for similarity of handwritten digits or letters. And also another interesting case is that it might enable people or programs to manipulate our system. So imagine that you have an algorithm which responsible for getting your money if you need a loan. So you came to bank and you give your information about you, and they decide, or program decides on based on something that you can be awarded with loan or no or not, and you are asking why. And if you know this algorithm, for example, that this algorithm is actually based on your daily income or your family's for your family status or anything, then next time you can try to make some manipulation to actually get this loan. So you can get temporary job, you can make some fictitious marriage and anything and something for just for months, but this will help you to get this loan. So if you understand how this algorithm is working, you can manipulate it. So we have a few different approaches to interpretability, and intrinsic interpretability is when you actually build interpretable model at the beginning. So we have like regression, linear regression, which is very well known and it's simple and you understand how it works, or you have decision trees, not too long, when you also understand how it works, but just by building this tree. So this is the intrinsic interpretability of the model. So it was first class of models. And second class post hoc interpretability is actually treating the model as a black box model. So you have some model, you don't know what is going inside, and you try different method to understand how you can understand what is going inside. And also another interesting question is, what is an explanation? So explanation is the answer to why question. Why question? And it's more about how people think, not about how model works, but you need to well, get the explanation what is working. So, for example, why we have not been contacted by alien life yet, and what is the explanation? Well, maybe they didn't go through the Fermat filter. So now we will talk about interpretable model, and basically what I want to underline is how we can build this model and why it's interpretable. I will try to do it quite shortly, but just to set everyone on the same page. So the idea that we want to see inside the model is to see why the prediction was being made. And we want certain properties to be in this prediction. So we want to the prediction is fair, to ensure that models are unbiased. I hope you read in the news about the recent, I think, Microsoft model, which was very highly biased on image generation. Yeah, you maybe knew about this. That when you ask, for example, Vikings, it generated very diverse images of Vikings. So in every set of images, there was a woman and some people with not white skin, but different skins. So model was biased because it was trained to perform diversity. Privacy, protect sensitive information. It's quite interesting that some guys actually developed a jailbreaking technique, and what they actually did, they took GPT 3.5. It was about half a year ago, maybe more, and they tried to perform a special sort of attack, which is called they tried to fill the context window with some garbage to force model work incorrectly. So they ask her to repeat forever certain word, and model try to repeat forever this certain word, and then they ask some question, and model in answer, model give actually part of the initial data that on what its model being trained. And this part of information of raw data on which model was trained contained personal information about some lawyer and their phone and address and some part of some letter that was somehow happened to be in the training set. So the author of this paper, they claim that they could gather about 1% of all data on which GPT three, I think, was trained. And then they contact the owner, and owners close this hole, at least for now. So it's very interesting and important topic, because it's not just talking about how model should perform, or maybe how it's not working, but now this model actually contains sensitive information, and sometimes you can force you to reveal it. Robustness, many small changes not cause big response. Causality, identify causal features, and all this ensure trust, where we trust this model is actually working. How we can actually well, build trust when model is very well, not simple. I will not say simple, but you understand how it's working. How is it working? So when we talk of a simplest possible model, which is very famous, and people actually, well, researchers work with linear regression at least, I think, 300 years or something, and they know a lot about this. And this is probably the most in the most clear model that we can imagine. And well, and we understand that when you build linear regression based on set of points, you have a positive relation when you increase value of one line, and the dependent variable also increase, a negative relation in opposite. And also when you have well, the beauty of linear regression is that doesn't matter how many points do you have, a lot of points, you always can create a formula which translates all these points into just two numbers. And these numbers are slope and intercept. Slope and intercept is the two actual values which define this simple linear regression. Of course, if you have a lot of, if you have n features, then you have n plus one number. So this very simple idea that when you train linear regression and you look at this coefficients, and you can understand what feature actually contributes more to the response, because the bigger contribution, the bigger slope of this line. So also interesting point that you can look at linear regression from probabilistic point of view, and this is an example of such kind of duality from math, which helps you create better understanding and better interpretability of the model. So when you do everyone know about this approach, probabilistic approach to linear regression, when you have a distribution of points for every, let's say, x, here you have, well, we have only one point here, but imagine that you have a lot of points. You have a cloud of points, and you can imagine that you have distribution for every separate x, and then you will try to maximize likelihood of the linear function over these points, and you just introduce the noise, and we actually expect this noise to be Gaussian. And when we maximize likelihood, we can actually put it in formula and find the maximum, and the result would be the same as a result of linear regression. So this is where linear algebra meet probability, and they give the same result, given that your errors are independent and Gaussian. So this way actually helps to understand that if you have even simple model, you can you can see on this model from different views, and you can understand better what is going on. So when you have a regression problem where as I said, in supervised learning, you have regression and classification, and you can use also regression for classification, but usually for this you use logistic regression. Anyway, logistic regression is also very simple and interpretable algorithm. You just maximize your likelihood, and instead of this line, you have this curve, and this curve actually assign probabilities of point to be class 1, 2, or in multi-class. You can also use it in multi-class classification with special function. So that's this algorithm is quite simple and understandable, but we can go further and we can introduce actually technique which called regularization. And this regularization is actually, by the way, when you have this model like this polynomial model, it's still linear regression because you can just assign x square as a new feature and the dependence would be linear. So it's still linear regression with respect to coefficients. And why you need regularization? Well, you need regularization because sometimes it helps you to get better result. Better result. By better result, I mean better error on the evaluation set. I will get to this a little bit later. So regularization is actually interesting technique because it is relevant to our topic. As you know, you can have two types of regularization, L1 and L2, and I will remind you that L2 norm, L1 norm are like this. And in machine learning, you can use machine learning with L1 or L2 regularization. And if you have linear regression with L1 regularization, there are special names for this. It's called lasso regression. And if you have linear regression plus L2 regularization, this is called ridge regression, or sometimes Tikhonov regression. So why it's relevant? Because well, I actually wanted to have some conversation or talking to you because it's not easy to read lecture to how many for 13 no 12 round square black squares. So what's the effect have regularization on the coefficient of regression? Do you know? So if you, yeah.
I guess, okay, to all the participants, you can use microphone for this lecture, or just write in chat in the Zoom. It's gonna be the best.
But do you know if you have this regression in form with lambda and you, for example, increase lambda, what effect it will have on your coefficients in lasso and ridge?
And also we get more zeros, like we just zero a lot of elements. With ridge, it's not that like harsh. It's a smooth function after all.
Well, in ridge you will never get zeros because they will get exponentially to zero. They will decrease exponentially to zeros. In lasso, you're correct. We will have a lot of zeros, but it's important to understand that it still tries to minimize the error. So this means that you can use this for feature selection and you left the most important features. So features which are not important for in terms of error, they will disappear and you will left only important features. So you can use it for feature selection to understand what features are actually important for our regression model and what features are not so important. So this way, LassoCal can be used for interpretation of the model. Second model is a tree-based model. So regression is very good, and you can solve a lot of different problems with this. But sometimes you need to split decisions. You can make decision. So when your relationship between features is highly nonlinear, like, I don't know, discontinuous even or something, then you better use a tree-based model. So very shortly about tree-based model, you have origin, decision node, and you have leaves, links, and you have split on each step. You have split, and you have special value how to split, and you try to split on each step, trying to minimize mean square error of the result. So you predict something and you try to minimize this. So you look for split, looking for splits, you choose different splits, and then you compute mean square error, and after this you choose the best possible split. So at the end you will end with a tree like this, and this way we can actually go to the situation where we'll have 100% accuracy. Yeah, 100% accuracy. It's really easy to get on training set, of course, using decision trees. So why we can't use this? Why we can't use this approaches, I mean, linear regression and decision tree, if you understand them so well, and why we can solve? Because, well, because complex problems are highly dimensional right now. So it's not easy to use this method. They have a lot of data, so your linear regression will be very slow. And also this method, you always need to fight over fitting, because, for example, last, I believe GPT-5 or something, these models, large language model, have now about 10 billions of parameters. So you can imagine model with 10 billions of parameters, and how it's not overfitting. Well, how it's possible even. Well, back before in 19th, I think there was a vision that you better not use a lot of predictors, because if you have a lot of predictors, your model will overfit. But now it's not the case, because you have this regularization technique and you have a lot of data. And if you consider the example of high dimensional object, we will start from very simple regression, a taxi ride from New York data, famous data set. It's a 7-dimension. If you take MNIST data set, it's early 90s, I think, which was created to recognize letters from post office. It's a 784-dimensional object. You have this number of pixels. If you take ImageNet, it's already so this one object on the ImageNet have about 200,000 dimension. You have 3 channels, 3 RGB channels, and you have different for each channel. But LiDAR recording have a few million dimension, and human DNA have about 3.6 billion dimensions. So that's why we need to have more sophisticated model. And when you try to create dimensionality reduction, you have different approaches. For example, this is UMAP and t-SNE. So t-SNE actually helps you to reduce dimensionality of your data, but in process, it completely ruin structure of the data original. and you no longer can understand how your predictors are related and how they influence each other. So it's very unclear process, and this is a very nice project. If you didn't know about this, you can how can I just copy it to you, so you will have some time during the presentation. So this is for example, visualization of vector visualization of a MNIST data set, where you can take initially these letters, and you see some of them closer to each other based on the distance of similarity, and then you can try to implement some PCA to get these clusters differently and separate them eventually. So again, when you have this data set and you need you take your data, you split it, you train your model on the train data set, and then you test your model on your test data set, and you understand, is it good or bad? And usually when it's complex model, it's really not easy to understand why it fails or why it is working. So overfitting is our problem, one of the many problems. So if you have a simple model, then you have some error on your train test and maybe test set. But when you try to go to real data, your model can be very bad. So if you overfit it. And one of the way how to do not allow this is to use, for example, random forest or use cross-validation. So as you know, probably random forest is by definition use some use techniques which are close to cross-validation. So you don't need cross-validate random forest. You always have the good results. So random forest probably is the most simple idea what you can perform if you don't know anything about your data. So cross-validation is the idea that you take your training data, you put it on folds, you use, for example, 3 folds here for train, 1 to val, and then you move over your training data. And this way you squeeze everything from your data which is useful to train your model. So and probably last reason why we need interpretation and why we can't use just simple models is the success of deep learning. So deep learning, well, as you know, it's a funny story that I think, well, you're probably aware about AI winter. Yeah, you know what is it? What is it? What is AI winter? It's a drop in when you have initial success and a lot of interest to artificial intelligence and methods, and then after some, well, delay in new invention and researches, then the interest start to drop, and everyone say, oh no, it's not interesting, we will not get anything. So first AI winter, one of the contribution to first AI winter was a paper, and this paper actually claim that if you take one layered perceptron, you can't actually model XOR function. So it was quite famous. Yeah. So it was quite famous paper because, well, if you take one layer per perceptron, you have XOR function, and you can't actually use this. You can't theoretically, you can't model this function. And after this, interest to artificial neural network or just neural networks drop significantly because they say, okay, it can't even model a XOR function. What we can do with this? And then I think Kolmogorov or something, well, there's a theorem that if you take two-layered perceptron, possibly infinite or a lot, a big, then you can model any function at all, approximate at least. So there's a very, very unexpected drop from inability to make XOR function with one layer, but ability to approximate any function with two layers. It's very, very unusual. So at some point, also if you didn't knew about this, you did not know about this playground, this great TensorFlow that helps you to show how this network is working, how it's trained, what's the output, and how you can combine different networks to actually train a model. And basically the basic idea is that you just connect neurons and you have a nonlinear activation function, and this nonlinearity of activation function actually and big scale creates you a complexity enough. And very famous step through, which happened to be in this year, where Alex Kryzhevsky modestly proposed AlexNet along with Sutskever and his supervisor Hinton, Geoffrey Hinton. So they propose the AlexNet architecture, and this AlexNet architecture actually on this challenge of ImageNet classification shows a very, very big improvement. And after this, they actually solve this problem with these deep neural networks very good. So, and it's actually, it's not easy for even for human to distinguish correctly, but the model already does this. And it's not easy to understand how it make prediction, but later they create some way how to, well, you can find the silence map, what actually features are contributed to the decision that this is a dog or cat or plane and or something. So when we have, after this, we have like explosion of different architectures, and all these architectures of neural networks actually do solve some different tasks better, or you have recurrent and convolutional and a lot of them. So, and I actually can advise you to listen Lex Friedman, because it's actually great about artificial intelligence and neural network. And to grow you deeper, well, to dig a hole a little bit deeper, I also add that you can take any of these models and create ensemble of this, and by ensemble you will improve your result usually. So if you have independent errors, you will always improve your result. And except ensemble, you can also create bagging, random forest, boosting, stacking, blending. So you can pack models into some voting schemes. You can connect them where output of one model would be input of other model. So it's really difficult to understand now how model make decision. So that's more the point. So when we started with linear regression and all the way to huge neural networks, now we can't actually answer sometimes. And a very nice paper, I like it. So these guys, they try to understand, they build a model which actually classify husky and wolves. So they had two classes, Husky and Wolf, and the model actually worked very well. But then they tried to understand why it's working so well, and they tried to dig into this model, and they understand that the reason why it's actually predict wolves better, because wolves were always on snow landscape. So the prediction was based on the landscape behind the actual figure. So when we talk to practical thing, we have a machine learning model, and this model has a set of features, and this feature is multidimensional space. And the objective of the model is to minimize some function or maximize the likelihood. So it's like a game where different features try to contribute into this objective to get the best possible result. And now we are going to our topic. When we have this feature attribution model, when we try to understand what feature contributes best to the result, we need few properties which are good to have. That's consistency. So if we change our model, so the weight of this feature will grow, then the importance of this feature should not decrease. So if we increase importance of the feature, then the weight of the feature, then its importance should increase or remain the same. So if we choose some metric to measure the importance of the model, then each feature should attribute to this metric. So if you have feature which actually do not change the metric, then this feature should not be considered as meaning as that have meaning. And we need to understand how feature is contributed to the objective. Is it lower or higher output? And when we talk about model interpretations, there are right now a lot of models. So first is model-based methods of interpretations. And this is what we talk about when we consider trees and regression. So regression is simple model, so we can understand that when we increase something, then depending on the slope of connected with this feature, we will increase or decrease the result. So it can be used only for simple model. Model agnostic, they treat model as a black box. So here we have three different types of method. Example-based, the best way to explain example-based is to remember k-means, for example. Yeah, when you have k-means algorithm, you decide about classification based on the nearest neighbor. Nearest neighbor. Sorry, nearest neighbor. So you make decision of class based on your of similar points, similar in some metric. So this example based. Global when you have some well, you try to understand something about the model, but I will not cover this. And local model agnostic methods is Shapley values. So what is a Shapley values or Shapley values or SHAP? So SHAP is a Shapley additive explanations, and SHAP is a Python-based module, which very useful, and it was proposed by these two researchers, I think, in 2017 they published at NIPS this paper. They publish at NIPS this paper. I can send it to you, so you will Take a look. And the idea that they propose a nice way how to calculate the Shapley value fast. So that's their main contribution, because the idea of Shapley value was before, but it required exponential time to calculate. So if you have a large model, it's not practical. It wasn't practical. So what they actually did, they took this idea and they found a very nice and fast way how to estimate it. So now we will talk a bit about Shapley value. So Shapley values is a concept from cooperative game theory. And it was introduced by Lloyd Shapley in 1953 by Lloyd Shapley. And the idea was to understand how we can evaluate a contribution of player to a team of players. So if you have some, well, we will take about this. In machine learning, it's about features. So we imagine that each feature is a separate player, and when you take features for prediction, you form a coalition of features. So this way, we can say that some coalition of features actually produce a more or less correct prediction. So when you add new features, your prediction will change and ideally will improve. So if you use all features, you will have the best possible, for example, prediction. But if you remove one, it is possible that your prediction will remain the same because this feature actually didn't contribute. So the value of this feature should be 0 because this feature is not contributing to our coalition. So let's get few examples from game theory so you can understand better how to calculate the Shapley values. And I will start with I have actually talked for 50 minutes. So let's imagine the game where you have 3 children and they want to buy as many candies as possible. And they have 3 options. They can have 50 grams, 750 grams, or 1 kilo. And the cost of these packages are 7, 9, and 11. But the children, 3 of them, they have 6, 4, and 3. So no child can buy package himself. They should gather. They should combine their features or their forces, and they can buy something. But the problem is that they need to divide the candies after this. And how to define fair division? So let's say you need to divide. What division you propose? So as you see, no, 3 of them can buy 1 kilo, but two of them can buy 750. So, and no one can buy. So to create to solve this problem, some formalism is actually provided. I will introduce you a bit. So the idea is that we will define special value function, and this value function will tell us the quality of coalition. So is it coalition better or worse as another one? We need a special function. In machine learning, this function can be error or likelihood. So we have a function which actually calculates the quality of coalition. Yeah, but they can buy more. So if you have no player, the value obviously 0. If you have coalition of separate player, the value would be 0 because they can't buy anything by themselves. But coalition of first and second player can buy this package. Coalition on first and third player can buy this package, but coalition of second and third can buy only this package because they have less money. But all three can buy this. So the simplest idea, very simple idea, is that we need to create a set of linear equations, and we need to calculate the division in the way that if you form, if you have, for example, coalition of three players, they should get something, x1, x2, x3, but this can't be less than they have in other coalitions. So if first and second have 750 together, they can't get less in this coalition, because otherwise they will separate and say, we will better form our own coalition. Okay, is it understood? And solving this equation, we have this division. First one should get 500, second 250, and third 250. And this is division according to the core, the conception from game theory. It's not Shapley value yet. The problem with the core is that sometimes all solutions are in the core with this idea, sometimes no solution in the core. So it's not good concept for any games. So that's why Shapley proposed another idea. And also, I will start with a very simple example, and I don't want to scare you with this formula. You'll find it in Wikipedia, for example. It's combinatorial formula. So the idea of Shapley was like this. He said, let's imagine that we fix some properties that this fair division should have. And he formulate 4 properties: symmetry, efficiency, null player, and additivity. So this property, which as he saw it, should be for fair division. And then he found, actually, theoretically, that only one division possible if it's fulfill all these properties. So it was result of Shapley. So he found that the only way how to divide according to these properties. And I will tell you this idea. So imagine that we have 3 companies, and these companies want to build airport. And they need length of, road to something, it doesn't matter. So first company need length of road, or maybe this launching ground of length 1, second need length 2, and third need length 3. And each part costs 100. So if they build separately, then first company will spend 100, second 200, and third 300. So together they will spend 600 of something. But if they combine their efforts, they will spend only 300. So it's 300 extra bonus. And they need to understand yeah, but it's interesting point, but not sometimes not working every time, because sometimes they can say, okay, we will form better coalition without you. So how we can divide this bonus between the companies? Obviously, they are not the same from one point of view. They are different. But from other point of view, all 3 need agree with something to start building. And by the way, in non-cooperative game, every player make decision at the same time, and by themselves. So that's why it's non-cooperative. In cooperative game, we have different setup. In cooperative game, we suppose that the players start negotiating, and when they agree to something, they sign some treaty which is non-breakable. So we have like outer force which helps to support this treaty. So if they agree to something, we think that that's it. They will get the same. They can't go out in the process. So the idea quite simple, but maybe you can propose something. So the idea is that we have first segment of this rod. Okay, we have first segment of the rod, and this segment is used by three of them. So they need to divide the cost equally. Then we have second part of the rod, and this part of the rod used only by second and third company. So they should divide the price between them. And the third segment is used only by third company. So the third company should pay the full price of it. Very natural idea. Do you agree? Yeah. So that's idea of Shapley values, but Shapley did it for general solutions, so it's a little bit more complicated. Okay. So the solution is that we form coalitions, and for each coalition we calculate a value which this player add to coalition when it comes to it. So at the beginning we have like 0 coalition, then we have coalition A came. Well, here it's in terms of not gaining but spending, but the idea is the same. Then B came, and he had 100 because A already built 100 rod, and then C came. So we have different coalitions, and we calculate this called marginal effect, I think, of the player to this coalition, and then we make average over all coalitions. So this way we calculate the overall value. And now, okay, let's go to SHAP. So SHAP is the package which allows you to explain how different features contribute to the general performance of the model. And the idea is like in Shapley values. So you form coalition of features. So for example, you have n features. You fix n minus 1 feature. Yeah, you use data for these features. And for last feature, you take the average of this feature as a predictor. And then you compare result with feature and without feature. So this way you calculate what contribution this feature made to the coalition, and then you make average over all possible coalitions. So let's, well, formulas are, I will send you this formula. So if you have some linear regression like this, you can calculate the features here. So contribution of feature to the overall formula is based on the using this feature and using just average of this feature expectation. And this way we can calculate overall coalition. So we calculate value of each player to this coalition with player and without player. And let's see how it will help us to understand something about the, well, I choose Titanic dataset. I hope you all know about this. So you have survival Titanic, and you have like age distribution. It's simple. You have survival rates based on class of the passenger, and you have, for example, survival rate based on sex and cabin class. So as you see, third class male almost all perished, second class, almost all female actually survived, and so on. But when we start to build these trees, it's not easy to understand why it's working this way. So what we can do, we take SHAP, yeah, and we create explainer. And explainer will depend of the model you actually using. So for all trees like XGBoost, Random Forest, and other, you use tree explainer. For linear models, you can use linear explainer. There is also deep explainer, many explainers here. And you can now build a plot which explains prediction for every particular passenger. So for each passenger, for example, we have actual functions that this passenger did not survive. So the actual prediction is 0.152 and the average overall passenger is 0.3. So this passenger is like worse than average. And what factors actually contribute to this, we can see on this image. So that's the idea of this feature contribution, and we can measure positively or negatively this feature contribute to the overall understanding. So this feature map, which heat map, which helps you to understand how different features contribute. Also, scatter plot, which quite interesting because this is, for example, for childs. So if your age is less than 10, your Shapley value, which contributes to your survival, is increased. But for higher ages, it becomes more or less the same, and it becomes at some point negative. Price of the ticket also, if you have a lower price of tickets, so you have like cabin at the third floor or back at the deep down, then your chances are bad. So your fare actually shows that. And for example, if you have higher number of siblings, then this contribute negatively to your survival, but no or one sibling contribute positively. So this is positive contribution, this is negative contribution. And also having the parents also contributes slightly positively. You can also make a force plot, and this force plot for every separate instance, you can see how it comparing to base value helps survive. And you have decision plot, which basically is the same, but it helps you understand how it's cumulatively attribute to your survival or not. And quite funny, I think this plot is they take the actual data of the movie from the movie, and they calculate their survival. So as you see, this is Jack has no chances, Rosie has very high chances, and this guy has like toss a coin. It's about chances about this about. So that's it. I think that we can finish on this. I recommend you a book about interpretable machine learning by Molnar. So that's the idea. Unexpectedly, I think that machine learning concept actually helps to understand something about how machine learning black box working. If you have any questions and we have some time, then please. Maybe for simplicity, we can just use microphone.
Yeah, we have some questions. Okay, so the first one is, how prevalent is the post-hoc approach nowadays? Anything deep learning is a black box mostly.
What's the beginning? Because I didn't
I'm sharing the
hear.
screen at the moment. How
Okay.
prevalent is the post-hoc approach nowadays? Anything deep learning is a black box mostly.
Well, yeah, deep learning model are mostly black boxes because they're huge actually, and well, you can actually you can take a look inside. You can see every weight on every link, but it will not give you any meaningful information because you have like billions links and you have weights. So to understand something, you need special efforts. You need to build extra model to understand what features I actually contribute, for example, for image recognition. Yeah, and this is done. So you can actually take a look inside and you can find the features which actually contribute to the to the image recognition. For example, we know now that for face recognition, the most important is the eyes and the nose area. So if you only look eyes and part of nose, it's enough to build a good recognition. So now we understand this. But if you, yeah, complex model are mainly black boxes.
Mhm.
Any other?
Okay, yes. Would Shapley values help with hyperparameter search, some sort of alternative to grid search?
Well, the problem with Shapley values is that you build estimation, because for original idea of Shapley, you need to cover all subcoalitions and all combination of subcoalitions, and this factorial numbers. So even for like 32 parameters, it's already millions of combinations. So we use Monte Carlo or kernel methods to estimate, but sometimes this estimation is not correct. So we need to understand that we can explain value influence of certain parameter, but we cannot explain the like real world situation sometimes. So I don't know about uh, replacing hyperparameter search. For now, as I read about this, it's about explanation and interpretability, uh, how different uh, how different features contribute to the result. Maybe we can, well, I think it's definitely interesting idea to explore. I can't answer right now, is it done or not, but I think we can try.
Okay. The next um, question for the end. Is it possible to convert black box models to some innately interpretable model? Is it a viable way? Have anybody tried it?
Yeah, it's actually, I think it's one of the trustworthy AI or explainable AI. It's one of the growing line or trend in research, especially with Europe regulation, where they actually they oblige uh, developers to explain how this model actually make decisions, and mostly people can't explain, so they try to put efforts into understanding how it's working. But we need to also take into account the complexity. So if you have a complex model with like billion of situations, it's obviously you can't just do the same with simple model. Yeah, you can go towards understanding how it's going, but you can't describe huge complex model with very simple model accurately. It's not possible. So you need at least the same level of complexity. Maybe you can use a lot of simple models to explain very difficult complex model, and maybe it will be enough. So uh, answer is I don't know. So I don't know. Is it possible to actually decipher any black box black box model. I hope so.
Thank you. Next question. So can we use fast SHAP algorithm for neural networks? Does it work with non-fully connected layers like convolutional ones?
Well, there is an approach called DeepSHAP, which specifically developed for deep networks. And I think it's possible. Maybe it will take a lot of time to evaluate, but it's possible. And you can, I think you can use it.
Okay. Next question. How computationally intensive is the calculation of shapely values? Can they be included at a pre-processing step for feature selection?
Well, it depends on model. I think they actually improve it, especially for tree-based model. So for tree-based model, it's like really fast. Uh, I, I don't remember. I think it's maybe less than polynomial or something. Well, polynomial is it's quite big, but I don't remember exact number. So linear and tree-based SHAP are quite fast. For other, you need to check the specification. I think it's more, well, it's getting worse when you have a lot of parameters, obviously. So it depends on the model, on your model and the size of your like training set and everything.
And the last question. What do you think about OpenAI Super Alignment project?
Oh, I think I was too busy with other things to I didn't read about this. So what is the project? Can you explain a bit or at least say something? Because
As I
I don't.
remember, it's they try to train some model that's gonna align their huge next large language model with
Everything to
alignment.
everything. They, as I
Uh,
remember, they wanted to create model which transform, which is everything to everything. So it takes on the input video,
uh,
uh,
no,
text.
that that was the model like for alignment purposes. So the model like don't do some crazy stuff that wasn't intended by creators of that model. So
No,
they
no, I can't say anything about this, but what I can say is that this LLM that was developed before, right now they're jailbreaked a lot, and I had a lecture about jailbreaking of LLM, and sometimes it's very interesting because they use the human-based reinforcement learning to fine-tune it to forbid certain answers, for example, how to make a bomb or
yes.
some drugs, or my favorite question is how can I take a stop sign and take it home? And initially it doesn't answer these questions, but if you put some jailbreaking efforts, for example, use ASCII art to hide it, or play some games, or use universal suffix, then it actually answers this. So I think that large language model, if you try to attack them, they are very weak. Yeah, sorry.
Okay. Thank you very much for
Yeah,
an
thank you
interesting
for
lecture.
invitation.
Hope it's gonna be
I can
helpful.
I can share a presentation later. Yeah.
Yeah, that
So
would be great actually. So thank you very
okay,
much.
bye. Bye. Have a nice day.
Bye.